My name is Justin. This is Lab 5, Faraday's Law. In introduction, our objective is to observe the behavior of a falling magnet through a conductive tube. Next is to model the interaction using growth script. And then finally is to compare that model with our observational data. Important principles involved are Faraday's Law, Biot-Savar's Law, Newton's second and third law, and Lenz's law. And the results from my observational data is that the bar magnet took an average of approximately 1.2 seconds to hit the ground, and the computer model predicted approximately 2.1 seconds, a significant difference. To start this lab off, we use aluminum foil because it's non-magnetic, unlike Phys's metals, which are magnetic. We're dropping this bar magnet into a tube, so we do not want the bar magnet to stick in the inner walls of the tube, so we choose a non-magnetic metal, such as aluminum. The dimensions of my aluminum foil is showcased here, also my magnetic bar. And here are the measured exit times. And important observation is that when we drop the bar magnet in this tube, we had a delay, unlike it would if I dropped it in free air. So there's something happening in between when the bar magnet's in the tube. So we know the bar magnet has a magnetic field, and that magnetic field is going through an area such as the tube. And when the magnetic field goes through an area, it creates a magnetic flux. We know from our observation data that there's a delay. So there must be a change in velocity as the bar magnet enters the tube. So a change in velocity means a change in magnetic field, and that means a change in magnetic flux. So we use Biot-Savar's law to find the magnetic field, and we use Faraday's law to find the change in magnetic flux. Moving on to the next tidbit of the code is that in this snapshot, we calculate the magnetic field in the ring portion of the tube, and then we calculate the force applied on the bar magnet when it's inside the tube. We know there's two forces. There's a gravitational force and there's magnetic force. We sum those up to equal the total force applied on the bar magnet. And then the third step is using Newton's second law, the momentum principle. We can calculate the bar's magnet velocity and position during its time in the tube. And here's a graph showcasing the bar magnet's lifetime in the tube. So the beginning and the end of this graph showcase that the bar magnet's velocity is increasing due to gravitational force. This is before the bar magnet enters the tube and when it's done going through the tube. And then the plateau part of this curve tells us that the bar magnet's velocity is decreasing constantly by a magnetic force inside that tube. In comparison of the times, the real life simulations and the computer simulation differ quite a bit, and this differs due to the computer model having a lack of human error and no air resistance. And so here's the simulations I got from my code. As you can see, the bar magnet is dropped on its north side. So the red of this part of this simulation is only present when the bar magnet's in the tube. And this red is the counterclockwise current. And I know that because due to Lenz's law, we know that the induced current is opposite of the change in magnetic flux. So if that bar magnet was to be flipped, the currents will also flip direction. And in this case, the red would be clockwise, and the blue will be counterclockwise. So additional questions is that if the resistance of the current of the conductor was close to zero, the induced current will be stronger Thus, the falling magnet will be in the tube longer. And then if there's holes and cuts in the tube, the total induced current will be lower. Thus, the falling magnet will reach the ground faster. So in introduction, we simulate an induced current. We apply essential principles to create a model, and we know that the direction of induced current is opposite of the direction of the change in magnetic flux. Thank you.